Welcome back. This will be our final video in this mini-series on advanced optimization techniques. Our previous videos went over how to impose constraints in regular nonlinear optimization and also how to supply an analytical gradient. In this video, I wanted to cover a tool called Mathematical Programming with Equilibrium Constraints, or MPEC, colloquially called MPEC. And this tool can be helpful if you're trying to find an equilibrium within an optimization problem, which comes up quite frequently in industrial organization applications. And the key idea is that instead of wasting time iterating in parts of the parameter space that are inconsistent with the equilibrium, we can impose constraints on the optimization such that it only guesses values that are in line with the equilibrium. It sounds great on paper. Let's check how it works in practice. And let's start by just talking through a little bit of theory, which is that if we have an equilibrium model, typically that's going to involve solving a contraction mapping. And this comes up with any sort of model that we want to solve for equilibrium behavior in. And in particular, very common in industrial organization applications and modeling strategic interactions among firms. And typically the goal is to estimate preferences for market entry or market exit that are consistent with the equilibrium model being asserted. So this becomes a contraction mapping. And if you remember from when we talked about the Rust bus engine problem, there was a contraction mapping in that problem to solve for the fixed point in the infinite horizon state space. The value functions had to be at a fixed point because there was no way to do backwards recursion because the horizon was infinite. So the same type of steps happen in other manifestations of the contraction mapping. We have to take a guess at the parameter values, then conditional on those parameter values, solve for the equilibrium, which means to find the fixed point of that contraction mapping. Then we just repeat this again with new parameter values and so on until it converges. And this is just like the NFXP algorithm that we talked about with the Rust bus engine problem. An alternative approach is to say, well, let's put constraints on the values that the parameters could take on by telling the optimizer what the equilibrium is that needs to be satisfied. And then maybe the optimizer can make smarter guesses about the parameter values. So this technique is called MPEC, where basically you're recasting the equilibrium as a set of optimization constraints, and it's going to make it easier to find that equilibrium. So typically you're going to get a speed up in the estimation because the optimizer is being smarter about its guesses. There's a famous paper in 2012 in Econometrica that showed this and went through the Rust bus engine problem using MPEC versus the regular approach. It claimed dramatic speed improvements. However, 4 years later, a large number of co-authors, including John Rust, published a rejoinder that showed that it wasn't a fair horse race in the Su and Judd paper, and that the optimization performed pretty similarly regardless of which method you used if you set it up in a way that they were comparable. So I'm not sure where this leaves MPEC as a method. It still sounds like it's useful to me, but I'm not doing these fixed point contraction mapping type of things in my research, so I don't have much other perspective to provide. It does look like it would simplify the problem, but maybe there's an additional set of difficulties in setting things up so that the constraints are adequately reflecting the equilibrium. Let's go through a Julia example that could use this MPEC concept to solve a very simple game theory problem, and that's the Cournot oligopoly, and more specifically the symmetric Cournot oligopoly. And there's a add-on package to JuMP called Complementarity.jl that's going to support this MPEC functionality. And we have an n-firm symmetric Cournot monopolistic competition problem, and each firm is choosing the output subject to their beliefs about what their competitors are doing. And then in equilibrium, the beliefs need to converge, and that's the definition of the equilibrium. We assume that there's a constant marginal cost and that it also is symmetric across all firms, and that there's some linear market demand curve This is something you'd see in an undergrad game theory class or maybe even an undergrad micro theory class. We know what the solution is to this problem analytically. It's just a function of the market demand parameters and the marginal cost and the number of firms in the oligopoly. But as is my custom, it's good to start using a tool on a problem where we know if we got it right before we want to start using it somewhere else. So let's show how to use this in JuMP. So basically we can formulate this as an MPEC problem where firm 1 is minimizing its negative profit subject to the other firm's first order conditions. And then we impose that everything's the same in equilibrium because the players are all symmetric. And then we can find this equilibrium numerically without any nested fixed point iteration that would otherwise be required. And then once we have this code, it's pretty easy to extend this model to add some sort of capacity constraints where the quantity that the firms choose is within some range. We could easily change the number of firms. We could allow asymmetric costs, so each firm has its own marginal cost. We could specify a nonlinear market demand function. And so it's nice to have sort of this basis to go off of before branching off into these other richer realms. So let's go through the code for this and show how it works. I've got a fairly simple script here. I just need to load JuMP and IPOpt. And then here I'm just specifying the parameters of the problem. So these are the defaults for the problem. Basically, there's no capacity constraint, and the market demand curve has these parameters. Everyone has a marginal cost of 20, and there's 7 players. And then I just specify firm 1's output as a variable, and then the other firm's outputs as other variables. And then we do have to choose an equilibrium where everybody chooses non-negative quantity. So we have to have those constraints. We also have to have the constraint that the market supply is equal to the sum of each firm's supplies, and a constraint that the quantity chosen by each firm is symmetric. And then we specify the profit function here, which is actually the negative profit function, which is total cost minus total revenue. And then we add a nonlinear constraint, which is the other firm's first order conditions. And then we optimize that and then just print the output. So it's pretty simple, but still pretty powerful. And so I'm calling it with a bunch of different parameters. So I call it without any constraints on the queue. I then put a random constraint of 17 on the queue for each firm. And then I up the players to 15. So let's run this and see what happens. All right, it ran. The profit in the original case is 50. That's the negative of our objective value. Every firm chooses a quantity of 5. The total market supply is 35. And then based on the demand curve, the market price is going to be 30. And that matches the analytical equilibrium. If we change the upper bound on the quantity to 17, that's not going to change anything about the problem. And then if we instead do 15 firms instead of 5, the profits are going to go down and the quantity supplied by each firm is going to go down, but the total market supply is going to go up and the price is going to go down. So again, this is all consistent with what we know, and that's a way to use JuMP to impose constraints without having to fully solve the model. So thank you for joining this mini-series on advanced optimization techniques. I hope you found something helpful that you could use in your own research or in evaluating the research of others. And at the very least, I hope you're gaining an appreciation for the work that goes into producing estimates of some of these more involved structural models. Thanks for watching and happy coding.